Right there. Now we are recording officially.
Mhm.
So I guess we'll let Aaron join us when and if he does. Um,
Anybody send him a message yet?
no, okay. All right. Well, let me attempt the demonstration first. So I guess I've got to switch cameras here. I think this will work. I haven't done it quite with the. Um, okay. Now, so here are ordinary 3D glasses. And what I want to do is show you the parts of what make them up. So you have to have a way of creating circularly polarized light and then a way of analyzing circularly polarized light. And okay, so there's a diagram in your book. This isn't quite the right one. I guess they don't have a diagram. No. I wanted to see if he shows one. I just realized this wasn't quite what I was looking for, but I think we'll work with it anyhow. It's hard to draw these pictures. They have to sort of be three-dimensional. But if you look at this figure in your book, this is from page 360 if you wanted to look it up. There are materials that can serve as a sort of retarder of one or the other polarization. So the two polarizations don't travel through the material at the same speed. And if you take light that is linearly polarized coming in, I don't know if you can, how well you can see this diagram, but here is light that is linearly polarized, but on the diagonal. So it still has vertical and horizontal components, but they're both in phase so that it's oscillating on the diagonal. These two would add up to create a diagonal wave, and then the one going back and the one going down would go the other. So it's going back and forth on this diagonal with both vertical and horizontal components. Then as the light passes through this material, oh, I've got some weird lighting going on. You guys seeing that flickering?
Yeah.
Yeah, well, you'll just have to live with it. I'm not, well, maybe if I turn that off, it might help. As it passes through the material, then one of these is delayed with respect to the other, with the result that when it comes out, they're not in phase in the same way. Now, we're at the beginning, the upward motion of the vertical component was in phase with the rightward component of the horizontal component, the rightward motion. Anyhow, as it comes out, the upward swing is in phase with a leftward swing now. So they just gotten shifted, and that's a shift of what would be called a half wave. So this would be called a half wave plate. We've shifted the phase of the two by half a wave, with the result that on the output, you still have linearly polarized light. It's just the other diagonal this time, instead of being the the first and third quadrants, it would be the second and fourth quadrants. That then one can imagine a material that take a piece of that stuff that does that and make it half as thick, and you would then have what's called a quarter wave plate. And if you did that, what came out of the other end, this is where I need a diagram that I don't have and I can't draw. Well, at least not without several hours of time to draw this. But you would have these two waves not shifted by half a wavelength, but shifted by a quarter of a wavelength. And that leads to circularly polarized light. And depending on which way you shift it, it's right or left circularly polarized. So what does it take to make circularly polarized light? It takes a polarizer and then one of these retarder plates. In this case, a quarter wave plate. Those two result in circularly polarized light. Now, the next question is, how do you analyze it? How would you make a detector that will only respond to, say, right circularly polarized light, that only lets through right circularly polarized light? Well, the answer is you just do these in the other order. You pass the light through a retarder, and you essentially shift things back to where they're in phase again, and then pass it through a linear polarizer that either accepts or rejects that. So it's the combination of a linear polarizer and a quarter wave plate that gets you linear or circularly polarized light. And then to analyze it, you do the reverse. You pass it through a retarder, a quarter wave plate, and then a linear polarizer. So now let's see if I can do this demonstration. I have here these two. One of these is a polarizer, and the other one is a quarter wave plate. Can you tell me which is which? I think this is basically like one of your problems, isn't it?
The left-hand one is the polarizer and the right-hand one is the wave plate.
Okay. Lucas agrees with you.
Yeah.
Eptahel hasn't weighed in yet. What do you think? Ben, why don't you explain why? Why do you think that's true? How do you know?
So, at least the logic that we had used yesterday on the homework was that the wave plate doesn't block light
Yeah,
as much as it transforms it,
right.
whereas the polarizer blocks half of any light hitting it.
Right. So you see half the brightness coming through this one, and this one looks essentially clear. You wouldn't know there was anything about it. It could just be a piece of glass, a very expensive piece of glass, I'd have to say. But anyhow, okay. Well, now what I can do is use these to create circularly polarized light. And so what I've got to do is start with the light coming through from the back side of it. We'll hit the polarizer, and we'll set it at an angle. I don't know if you can see, maybe you can see it now. Okay, there we go. We'll set it like that. You see that tiny little mark right in there? That is indicating the direction of the electric field that's allowed through. So I'm going to set that at about 45 degrees. That doesn't happen to line up with the numbers on here, unfortunately. I should take it apart and shift it around a little bit. It would be easier to use. But on this one, you can see another marking on here, and that's distinguishing between the two axes of the quarter wave plate. One that travels a normal speed, and the other one is retarded or advanced. I don't know which. So I want to set these two at 45 degrees from each other. And if I'm trying to create circularly polarized light, then I need to stack this one on top. It's the second one, so that the light comes from the paper down here up through them, and set those at about 45 degrees. And now you're looking at circularly polarized light. Isn't that amazing? Yeah, well, okay. Now, here I have a set of 3D glasses. Now let's see if this will work. It's not behaving as well as it did before. Come on. This was working so beautifully a while ago. What am I doing wrong? It must be an effect of the camera. Whenever the camera is on, things don't work. I had this working 5 minutes ago. It was beautiful.
Does the lens have a polarizer on it?
Say that again?
Is the lens polarized at all?
You mean these?
No, the camera lens.
Well, I'm not seeing the effect with my eyes either.
Oh, okay.
So I can't quite just blame it on that. I'm going to flip this around. That should not work. No, it doesn't. Okay. Oh, wait. I think maybe I know what we did wrong here. Yes. My mistake was to put the glasses on this way. That's the wrong way. Do you see?
Yeah.
I've got to flip them over as if I was going to put them on my head. Like so. They're toward me.
Oh.
And now,
Yep.
now you see the effect.
John, I think it was black when you were flipping it as well.
Well, try flipping it over, John.
Flipping
The lenses
Glasses.
over.
flip them over like this.
Yeah. Oh, okay, no.
No.
I know
Yeah,
it doesn't work this way, but it really does this way. And what's more, the orientation, it's not supposed to matter. I don't know why it does. This is hard to hold all this constantly. See, if I turn the glasses, that doesn't have much of an effect. I can't do this very well. Still more, another interesting thing one can do is just take two sets of these. And you don't get any effect like this. You have to flip one of them around. So if I turn these around, then you see the effect. Isn't that dramatic?
Oh.
So these work very well just all by themselves. And once again, the orientation shouldn't really matter. So you can tilt your head all you want when you're watching the movie. And you'll get the right effect. So there you go. That's the way that we go from ordinary light to a circularly polarized light. It takes two things to do it. It takes a polarizer and then a wave plate. Now, I don't know. It's possible that they actually do it a different way in these glasses, but I know at least that's one way it can be done. And the fact that all these experiments are consistent with that makes it more likely, though it's not entirely certain that that's how it's done. All right, let's take a look at a polarization example. I wrote this all out, and I'm frustrated right now because my camera isn't very high resolution. And so I can't quite do things. If I show stuff like this, it's going to be awfully hard for you to read any of those subscripts. But what I'll do is just work it out again. We'll just go through it together. So what I wanted to do was just talk about a polarized light in mathematical form. And so what if you have some light that has an X component that is sinusoidal, and we'll write that in the following fashion. That should be familiar to you as a typical way we write for a wave, but that's just the X component, and then the Y component would be something similar, except we'll put in a phase factor. Epsilon is what Hecht uses, and so we'll do the same thing. You could write this out as one vector form with I and J, but I don't think I won't bother to do that. There's no particular advantage for these purposes. So let's first just consider the simplest case where epsilon is 0. So there's no offset between the two. So both components are in phase. And what do we get? What sort of light does this give us? And what we will do is we'll look at z equals 0 and just see what's happening there. And everything else would just be sort of shifted from there. But let's look at z equals 0. And then we'll consider a bunch of different times. Let's start, of course, with omega t equals 0 as well. T equals 0. I'm just going to keep writing omega t because we'll do it as bits of pi over 2 and such. So at omega t equals 0 and z equals 0 and epsilon equals 0, this is all a bunch of zeros. And so you can see that the x component will just be whatever this amplitude is. It's just going to be E0 times the cosine of 0, which is 1. And the y component, similarly, is going to be the same thing. Since epsilon is 0, these two are going to be identical all the time. That's pretty straightforward. What about at omega t equals pi over 2? So let's wait just a little bit. And what would you get there? Can you figure it out? What are EX and EY in that case? Is this easy?
Zero and 0.
Yeah, that's right. Aaron!
Hey, sorry, I am just completely all out of sorts with this whole online thing.
That's okay. I just had a little fun with the demonstration that you missed. Oh, we've recorded it though, so you can look at it later.
All right.
So
Does it have to do
now
with
we're,
polarization?
yes, it did. I sort of figured out how these 3D glasses work and actually got a demonstration to work properly. It took me a moment. I did it wrong to start with. So now we're working through an example, Aaron, where we're just considering a wave of light that has x and y components. Kz minus omega t is our typical way of writing this. And there could be a phase factor, but for the first example, we're considering the phase factor of 0. And we just want to see what do we end up with. This is supposed to help you know how to do the very first problem. I think it's number 4. It's kind of like this. And so I thought I'd work through an example here. So Ebdel just said it's a couple of zeros when we get to pi over 2, because you just have cosine of pi over 2. Cosine of pi over 2 is 0. So these are both 0. So what about at the time when omega t is exactly pi? What are we going to have then? What's the x component and what's the y component going to be? So once again, z is 0, so the kz term is gone. Epsilon is 0, so it's just cosine of pi.
Won't it be negative E0 for both of them?
It will be negative E0 for both of them. Exactly that. And I guess for completeness, we could do one more. This would be, let's say, 3 pi over 2. And what would EX and EY look like then?
It'll be 0 and 0 again.
0 and 0. Very good, Lucas. Okay. Now what you can do is draw a little graph of what this looks like. So if you just make a little cross like there, here's your X and Y axes, and you've got equal components in each direction. So here are the X and Y components, and your resultant is going to be off at exactly 45 degrees. Down here, you're going to have a big fat 0 in the middle. In the third case, at omega t is pi, what do we have? Well, negative and negative. So we head off down this direction. And the last one is 0 again. So this is trying to illustrate that what we're going to get is linearly polarized light. It's just oscillating along this diagonal. The two components are right in phase, and you end up with this linearly polarized light. Okay, that's pretty easy. Let's do a different example that's a little bit harder. So I'll put this up here again. E0 cosine of kz minus omega t. And this time, let's put in a phase of pi over 2. Okay, so this is for pi over 2. And once again, consider kz to be 0. So we're looking at z equals 0. And start with the case of omega t equals 0. So what's the x component and the y component in that case? Now we have to do a little more work. So kz is still gone, and for this one at least omega t is gone. So the very first one is E0 cosine, yeah, it's just E naught. E0 cosine of 0, which is just 1.
And EY is 0.
And EY is 0. That's cosine of pi over 2. So we'll have nothing there. Okay, what about omega t is pi over 4? See if we can work that one out. EX and EY. What are we going to have? EX will be E0 cosine
of negative pi over 4.
That's correct. And what is that?
I don't know the cosine negative pi over 4 off the top of my head.
Pi over 4 is 45
over
degrees.
2?
Yeah, it's over the square root of 2.
Okay.
Yeah.
So I'm just going to write that as E0 divided by the square root of 2 in a way that I can write it out kind of in a line here so I don't have to run out of space. Then EY is going to be E0 of cosine of, and that's minus pi over 4 plus pi over 2.
Positive pi over 4.
Right. This in here is positive pi over 4, which actually makes no difference. On a cosine function, whether you're taking positive or negative doesn't make any difference. So we get the same answer. E0 divided by the square root of 2. Okay, let's keep going. Omega t is pi over 2. EX and EY, what are we going to get there? Yeah.
No, 0 and 1. So no, the
Yeah.
first one is
Yeah.
0.
First one is 0. This is the cosine of pi over 2. That's 0.
And the second one is E naught
Right. This is cosine
of 0.
of 0 ultimately. It's minus pi over 2 plus pi over 2. And that ends up being cosine of 0, which is 1. So we just get E naught again. Okay. Keep going. Omega t is 3 pi over 4. And this will be E0 cosine, and this time it's minus 3 pi over 4. And Aaron needs help with this one.
Is it negative root 2?
Yeah. E0, negative E0 divided by root 2. It's 1 over,
Okay.
but it's negative. You're right. You had all the right pieces there. You just didn't quite say it right. Then E0 cosine of minus 3 pi over 4 plus pi over 2.
You're off the bottom of your screen.
Oh, thank you.
Going to be E naught over square root of 2.
Yeah, and this time it's positive. Okay, that's enough now. We need to make some graphs to see what this looks like. So starting up here with the very first one, it's going to be just an x component, and that's of length E naught. Then over here, what have we got? Well, now you've got x and y components, both positive, but of length 1 over root 2, which leads to a hypotenuse that is exactly the same length we had in the first one. And then what do we have here? Well, this time it's just a y component of length E naught. And then what do we have here? X is negative, y is still positive. Both of them are the square root of 2, so that the length is still the same. You see how we have a vector that's just rotating. So the net result is this thing is just going around in a circle. And it has the same length every time. The magnitude of all of these would be E naught. So this is an example of circularly polarized light. And that's because the x and the y components are shifted from each other. Oh, this stupid thing is telling me this is going to end in 10 minutes.
And that is a L state?
Oh my, you're asking a good question, Aaron. I think you're right. I should know the answer to that. But having not read this for a little while, it is a pure circular polarization state. Yeah, what is that called?
He used the term L state and R state
L
for...
or R, yeah, whether it's L or R, I don't know. Let's see. The definition for that. This meeting is going to end abruptly. I will simply restart it, and we can all connect up again. How does one define which is right and which is left?
I thought he said something about it being, if it was in the direction of clockwise, it was R. The counterclockwise was L.
Yeah, but then you have
That was my recollection too.
Yeah, you have to say a lot more than just that. As viewed from which way? Yeah. I'm not going to be able to figure this out right now.
Okay.
Oh, here we are on page 334. I'm still not convinced I can sort it out. You have to know. So we've been doing it in time with X and Y, and the wave is progressing in the positive Z direction. Yes, that's right. We have a wave going in the positive Z direction, and then it's rotating. Yeah, I think we've got an L. I think this is an L polarization. Yeah. I hope that's right. Okay.
Need to start.
Let's end the meeting and restart so we don't get interrupted in the next one.